Sorry I couldn't be in person, but I'm super excited to give this talk to you. We're going to talk about embeddings. I'm going to cover the field, as much broadly as possible. I'm also going to talk specifically about some of the work we've done at OpenAI. Those work is joint work with many excellent colleagues at OpenAI. Cool. So let's get started. Embeddings, the terminology is actually overloaded. Think about a simple neural network. You have an input, and then the neural network does many layers of processing, often referred to as hidden layers, and then you get the final output, right? And embeddings here could mean any of these internal or hidden representations of the neural network. This is a general way the word embeddings is used. In this talk, I will use a specific definition of embeddings. Here, embeddings are used to denote the final vector representation for a particular concept. Okay, so think about an input, which could be word, text, code, image, or so on. You have a neural network encoder that has many layers of processing, and then you get a final vector. This final vector representation is intended to capture some form of semantic information about the input. Okay, so once you have this vector representation of a concept, then you can use it for many different applications. So let's go over a few high-level applications. So you get a vector representation of a concept. Then you can use it for a task like classification. So here you get a piece of text. You want to classify whether it's spam or not. You get an image. You want to classify whether it's a dog or a cat, and so on. So for all these all these types of tasks, you can use the embedding of the input and then use that as a feature for learning a classifier. Similarly, you can use it for data visualization. Clustering is one popular way to do that. So you have a collection of items. You compute vector representation or embeddings of those input, and then you do things like k-means clustering. The final application I want to talk about, and probably the most widely used one, is search. So you have a collection of items. For example, this could be a collection of text documents. And then given a query, you want to find the most relevant one. The way that works is you can take the collection of items offline, you can embed them, and then construct a vector database. The vector database helps you to scale to extremely large number of items, even 10 billion items or more. And then given a query, you embed that also with the same model, and then you look for the closest item in the collection. And this is how embedding-based search works at a high level. So embeddings are basically vector representations of input, and they have a lot of downstream applications. And that has led to a lot of research and other kinds of work in this field. I want to give a very, very brief history of embeddings in the last decade. Embeddings as a topic has been around, I think, as long as neural networks have been, artificial neural networks have been. So it's impossible to cover all the work here. It's impossible to cover even the work that has happened in the last decade. So this is going to be a super high-level summary of what's happened in this field. So I think a lot of the initial excitement in the last decade was on embeddings for word. So you have a word, you get back a vector. Word to vec was a method to do that attained a lot of popularity. And then there's relational data. So you have a knowledge base with entities and relations. You can compute vector representations for them. And then methods for computing embeddings for sentences became more popular. These often required task-specific data. So you get embeddings for a particular downstream task. And then even later on, we started seeing general purpose text embeddings. Here, you typically train your embedding models on just unsupervised data, and then they seem to work really well on a very broad set of tasks. And this has really created a lot of excitement recently in AI research and applications. And similarly, like text, you can compute code embeddings, you can compute image embeddings, and so on. So this whole field, I feel, has moved on from like starting with very simple embeddings for very simple concepts now to all the way to learning embeddings for any kinds of input, and these models have become much more general purpose. Okay, so that's a very brief introduction about text embeddings and embeddings in general. So now I'm going to move on to discuss how to train embedding models, and specifically, I'll just go over one particular way to train these embedding models that are now extremely popular. Okay, so I'm going to talk about contrastive training, which is basically become the default objective for training these embedding models. Lot of the the current state-of-the-art embedding models are trained this way. The way it works is you have you have a neural network that processes an input and gives you a vector, and then you have data in the format of pairs. So and by being in a pair, the two inputs in the pair are similar, are semantically similar. So one way to think about it is like, a paragraph and its, neighboring paragraph are similar. A text caption and the image are similar. Docstring and a code that implements it are similar. So these are all natural ways to get these kind of paired data. And then you want the embeddings of the two inputs in the pair to be close to each other. And that's like the basic assumption or intuition on how these models are trained. Before we move further, one point here is that the embedding models are optimized to learn a single embedding of the input. And this is different from most generative models, the thing like, things like ChatGPT and GPT-3, where they are like trained to predict some held out part of the input. Those models are not optimized explicitly to learn a single embedding, whereas contrastive training helps you have a model that's tailored to do this task of getting a vector representation of an input. Cool. So let's dive a little bit deeper. So you have an input, you encode that with a neural network, and then you get a vector representation. Okay. And then you have paired data. So let's consider the case of like text, and let's say you have query and document, and you know that this document is related to the query. So you want the model, the embeddings of these two inputs to be close to each other. And you can model the score by cosine similarity between the two vectors, right? So for examples that are in the training data for the pair, you run the embedding model in parallel for these two inputs, and then you get back a vector on each side. Now, to train these models, you need something more than just positive examples, right? Like, the previous slide, we talked about, the two inputs needing to be close to each other. And that's like basically positive examples. Now you need some negative examples so that you can tell the model, you want the positive examples to be more close to each other than negative examples. Um, and the way kind of modern work on training embeddings works is you basically use other examples in the batches as negative data. Okay, so while training machine learning models, we use mini batch gradient descent, right? So you have like some number of examples in your batch. You usually compute the gradient for each example, average it out, and that's how you do the learning update. So with contrastive methods, what you do is, given a batch where each example in the batch is a paired data, you use other examples in your batch as negative data for that particular input. So if you have a batch size n, uh, each example has n minus 1 negatives. A way to visualize this is like you have n examples. You can construct an n by n matrix, okay, where each diagonal entry is a positive example that has to be ranked higher than the other examples in the batch. So you actually start with n examples, but you end up with uh, n by n classification examples when you do it this way, right? And this turns out to be super crucial. And I think this is why contrastive methods have become very popular for training embeddings. Um, because now you're reusing the compute from the positive examples um, and like kind of using that as negatives for the other without having to do uh, computations to find out the embeddings for those negative examples. So you save a lot of compute and you kind of like blow up the number of like bits from which you learn the model. And I think this is like has been a pretty cool trick to train these embedding models. So given that the other examples in the batch act as negatives, larger the batch size, there is more chances that there are what is referred to as hard negatives. You know, you have uh, you have like lots of pairs that are not related, but you want like some like negative example that's like kind of close but is not as close as the positive examples, right? And then by blowing up the batch size, there is like more and more chance that there are some hard negatives um, in the examples you're contrasting against. And to give you some flavor on how this looks like is if you train two models and one of them has a batch size that's 10 times more than the other, we see a huge performance improvement for search task. This is like text search task. So this turns out to be another very crucial thing to do to make contrastive learning work. Okay, so we discussed embeddings. We dived into one of the ways the embedding models are trained. Now, let's discuss or let's summarize the training recipe so that it's easy to take away how these things work at a high level. Okay, so you have paired data. This is like, paragraph and its neighbor. It could be like docstring and its code and so on. You collect this paired data and then you contrastively train with a very large batch size. And that's it. It's quite simple. It turns out, though, just doing this is not quite enough. And this is because the contrastive objective on its own basically doesn't seem to have all the training signals that you need to learn from scratch. So in practice, we initialize this with a pre-trained model that's already for example, generatively pre-trained. And that's done on vast amounts of data. But this is it. It's only like 3 steps to train these kind of high quality embedding models. To make it more concrete, at OpenAI, we have trained text and code embedding models. We initialize them with a pre-trained model like GPT or Codex. We collect unsupervised pair data. So for text, it's like neighboring pieces of text in the internet, a paragraph, and it's like neighboring one, for example. And then for code, we basically take a comment along with the function as the paired data, and then we train with a very large batch size, and you get these pretty general purpose high performing embedding models. Cool. So we've discussed what embeddings are, how to train them, and like and a high level recipe for getting high quality general purpose embeddings. Next, I want to discuss a little bit on how people evaluate embedding models. I'll go through this by also talking about the performance of some of the embedding models we've trained. Okay, so let's start with qualitative experiments before diving into quantitative numbers. So here, this is as we discussed before, is one very popular application of embedding models, is to do data visualization. So you could take something like the Amazon fine dining review data set. It has a lot of reviews of different restaurants, and some of them are positive, some of them are negative. The data set has that information, like the sentiment score given by the user, but we don't use that for embedding it. We basically just take the text, we compute a vector representation, and to visualize, we did a two-dimensional projection of these embeddings, and then when we lay out that text in the two-dimensional manifold, and then color them, based on the review score given by the user, we find that the positive and the negative sentiment text is clearly separated here, and that's like great, right? Like we basically just used unsupervised data to basically for the model to learn about sentiment, and this is quite cool. Now let's dive into more quantitative tasks now. So one big application of embeddings is on classification, and here we're going to study specifically linear probe classification. What this means is, given a text input, we first convert that to a vector using the embedding model, and then train a logistic regression classifier using these vector representations as features. Okay, so the task could be something like sentiment classification. So you're given a text, say whether it's positive, negative, or neutral, and there's an eval library called CentEval that has kind of collected, or actually is like a evaluation suite that uses a bunch of data sets that different people have collected, and this is all open source, and it's a very convenient library. And when we run our embedding method on that data set, we basically get very good downstream classification performance. And so this is like one big use case for embeddings, and it's great that these models do well on that. Next, I want to talk about text search task. So the task here is, given a collection of documents and an input query, pick out the document that is most relevant to the query. Okay, and these document collections could be pretty big, tens or even hundreds of millions, and then in those cases we do the search with vector database methods. So we use this particular eval suite called Beer, which is again a very lovely open source eval suite for text search task. Again, we see that our embedding models perform quite good on this benchmark of search task. Next, we look at code search task. So here you're given a text query and a collection of code blocks, could be like code functions, could be a bunch of functions put together, and then the task is get the code block that is most relevant to the input query. So similar to the text search task we discussed before, instead of searching over text, now you're searching over code. Here we actually see our method works substantially better than previous work, and again, this is one of the more like kind of popular applications of these embedding models. The key takeaway message is that now it's possible to train a single embedding model that works well on a very broad variety of tasks. This is relatively recent, I would say, has happened in the last 2 years or so, and this has made the field super exciting. Now you don't have to have like one embedding model for this task, another for that task. How you manage that. I think it's basically made it has made applications of these embeddings a lot easier, and I think that's one of the reasons for the recent explosion of interest in embedding models. Cool. So this is great. We covered a lot of work on embeddings, what they mean, how to train them, and then how we've recently gotten to the stage where you can basically just have a single embedding model that works well across the board. Next, I want to cover one extremely popular application of these embedding models. This is taken off in the last year or so, and there's like so much work both in research and in applications. And so let's talk about this. So retrieval here means that you have some kind of private corpora, knowledge corpora, or so on, and then you want to enable people to talk about that corpora. Okay, so let me give a little bit of background on language models, right? So they've of course gotten super popular, lots and lots of excitement here from Google Bard to OpenAI ChatGPT and all these models, and these are basically what are known as generative models that are capable of generating text. One kind of drawback with the simple generative modeling approaches is that it's very hard for these models to remember everything, and it's also like factual stuff. Also, there are private documents, of a company, other kinds of knowledge bases, and so on, that the model is not trained on. But let's imagine you want to build a customer chatbot, you want to build like an assistant for your workspace. You want the model to know about that, and retrieval is a way to connect these language models to this kind of background database. Okay, and it's using this idea called retrieval augmented generation. I'll talk more about it, but this is like become a very exciting theme in recent times. So you have this, for example, Ask Y Combinator application that someone put out, where you can they retrieve information from essays from Y Combinator and Paul Graham and so on, and then use that use that to answer questions. There is one more called as librarian GPT, where it pulls out information from books so that people can talk about it. And so let's go a little bit deeper on how this method works. So you have a provided corpora, could be, in the first application we talked about, it was like Y Combinator essays and so on. You basically embed all those essays and build a vector database index of that provided corpora. Okay. Now, when you get a query from the user, you retrieve the relevant context from that vector index, and then while prompting the language model with the input query, you also add the relevant context you got from step one, and that's it. When you add that extra information to the model's context, the language models are capable enough to use that and generate responses that leverage that information. And it's a very simple procedure that basically connects two models, generative models and embedding models, to give out this. I I think it unlocks this very broad set of applications. And there is a whole ecosystem that's developing around this. One of them is Demonstrate, Search, Predict. This is from Stanford NLP group. There's LangChain, which is like an open source library that lets you connect these kind of search and generative models together. There's also, we've put out OpenAI Cookbook, has code examples on how to do this. We also open sourced a Retrieval plugin for ChatGPT. The use case for this is that you have ChatGPT, and then you can connect external data to ChatGPT using the Retrieval augmented generation technique we discussed, and this is all open source, and this way you can have ChatGPT consume and use private content. Great. So Retrieval is super exciting, and I think we're in very early stages of this new technology, and I'm going to spend few minutes on future directions that I'm most excited about. Okay, so the first one is joint training. So if you observed what happened before, we basically train these generative models and embedding models separately, and then like kind of stitch them together at test time. And that might not be optimal. A better way would probably be if we can jointly train, the embedding search component and the generative component. There's been a lot of early research in this area from many different companies and academic institutions, and like it's not gotten to the stage where it truly works. So there's still a lot of work. I think one challenge here is when you're doing gradient descent to train these models, the embedding search method, you can scale to a large number of documents but using the vector database, but then you can't really backprop, which is the gradient descent algorithm for neural nets. You can't really do that for the whole index. So you'd have to resort to some kind of approximate methods. Is that good enough? That's like an open question. Another question is what's the best way to train this kind of a joint system? With generative models, there's a lot of raw text in the internet, and you can make the model predict some held out piece of text. With embeddings, we discussed paired data. But is there some kind of data that's out there that is conducive to train these joint embedding and generative models? That's another open question that we have to figure out. And then the final set of work that is also very exciting is the way we set up retrieval augmented generation. You do like one lookup to the private data and use that information to the generative model. And that might not be good enough for some use cases. Imagine something like, when we use, for example, a search engine, we sometimes do a query, we look at the first results, and you're like, I'm not super happy. I want to like change the query a little bit. Maybe I want to go back and do another kind of query. And this is like, super helpful for us. And right now, the way these methods that we discussed so far work, there's no way for the model to do this kind of iterative multi-hop querying. So it'll be great to have something like that with our models. And there's some early work on kind of taking these generative models and making them more like an reinforcement learning agent, like where the model has a chance to do multiple queries, and they work to some extent, and I think there's a lot of work to be done there. And they also work in a way where you need supervised data, and then you're like getting that behavior by using carefully curated data. It'll be pretty amazing if we can learn this behavior of multiple multiple queries at pre-training step? And that's like a big open question. Okay, cool. So that's all I had. We discussed about embeddings, we discussed about retrieval, we covered a lot of ground. And yeah, thank you all for listening, and hope you all have a great conference.